This presentation is on the recursion theorem and the decidability of logical theories. My name is Patrick Ansel.
And my name is Jaren Musarat.
First, we're going to talk about the recursion theorem.
To understand how the recursion theorem works, we need to understand computable functions. A computable function is a function that takes a string as an input and returns a string as an output, such that there is a Theorem M that takes an input W and holds on W with f of W on a tape. For the next part of the proof, we will use a computable function Q that takes an input string W and returns P of W. Here P of W is a Tm that holds on any input with W on the tape. Now, based on the computable function, we will see how a self-reproducing Turing machine works. The goal is to create a Turing machine that writes its own description on the tape. We call it self. Self is made of two parts, A and B. Here self equals AB. It means the description of self is the description of A combined with B. In order, A runs first and then B. The purpose of A is to B, where A equals P of B. And the purpose of B is to print A and combine it with B to make AB. Here, P of B is a Turing machine that writes the description of B on the tape and then halts. Let's look at how B works. Here in the function B, we input M. So here M is actually the description of B itself. Inside, using the computable function, we compute Q of M to get P of M. And P of M is actually the same as P of B, which is also equals A. So next we combine the P of M with M to make a complete Turing machine. Then we print the Turing machine and then it halts. So what happened here is P of M is A and M is the description of B itself. And then since we combine them together, it makes a complete Turing machine that prints the description of A and B combined. Finally, self halts with our own description on the tape.
The recursion theorem shows that you can create a Turing machine that not only prints its own description, but performs a computation on its own description. And by performing a computation, that can be the computation of any computable function. So what we want is a Turing machine called R that on input W can print the encoding of R and W on the tape and then compute with it. So formally, it should halt with T of R, comma W on the tape, where T is any computable function of two strings. The construction of this is similar to that of self. R is made of three parts, A, B, and T. So self was made of two parts, A and B. R has three parts, and the first two parts, A and B, are what do the recursive stuff, and T is the part that computes the function lowercase t that's referenced here on the top line, where R needs to halt with T of R, comma W on the tape. So that capital T, that's the Turing machine that executes that function. A and B are what put the prerequisite stuff on the tape for T to operate on. So R starts with W on the tape, and we modify Q so that P of X, in this case, preserves what is on the tape before X. So we're using a modified version of P. So the Turing machine before P of X, in the previous case, it would erase whatever's on the tape, and it would X in place of it, and then it would halt. This new P on input W, P of X would halt with WX on the tape. So it kept whatever was on the tape, and then it wrote X after it. So A, in this case, is P of BT. So after A is run, starts out, before A is run, W is on the tape. After A is run, W, BT is on the tape. So that's the input to the program R, and then the description of B and T together. What B does, B is run after A. It applies Q to BT, which is on the tape. So that'll give you P of BT, which is the same thing as A. So now we have A on the tape as well. So we have A, B, and T all available to this thing. So it combines them together to get ABT. So now we have the input W available to us, and we have the complete description of the machine R itself, ABT. Because remember, R is the same thing as ABT. So it has W and it has ABT available to it. So now control is passed to T, which will compute lowercase t on the description of R and W to get its result, and it will halt. The statement of the recursion theorem and its proof are very technical, but what it means for you is that when you're describing a Turing machine as an algorithm, you are allowed to get the machine's description itself and put it on the tape and have it available in memory as something you can use. So you can see that here with the machine R, where the first line in this algorithm is to get its own description. That we can do because of the recursion theorem. That getting its own description is what the A and B do as the first part of the machine R in the statement of the recursion theorem. What T does, that's everything else. That's the computation that it does afterwards. A and B, that recursive stuff that it does, that we can just pack into a little statement that says get own description. The first application of the recursion theorem will be to show that this acceptance problem for Turing machines is undecidable. So this language A is the set of all Turing machines and inputs such that the Turing machine accepts the input. So it's similar to the halting problem, which asks whether M halts on W. This one asks, does M accept W? This problem is similarly undecidable. To show that it's undecidable, we use a proof by contradiction, so we assume that A is decidable, and we call the Turing machine that decides A M. And we construct this program called R, and we ask whether M accepts R and W. This machine R uses the recursion theorem to get its own description, and it's designed to make M give the wrong answer. So it gets its own description, and what it does is it runs M on itself and W, and it does the opposite of what M said. So if M said that R accepts W, it rejects. And if it said that M rejects W, it accepts. So the question is, does M accept RW? If it does, if M does accept it, then R will reject W because R does the opposite M says. So that means that W is not in the language of R, but W has to be in the language of R because M accepts R, comma W. So there's a contradiction there. And if M does not accept RW, then R accepts W because it does the opposite of what M says. So W is in the language of R, but W can't be in the language of R because M rejects RW. So either way, there's a contradiction, which shows that A is undecidable. The recursion theorem can also be used to show that this problem is not recursively enumerable. And the problem I'm referring to is determining whether a Turing machine is a minimal Turing machine. A Turing machine is minimal if its description has the fewest number of symbols possible. So that means there's no other Turing machine that has a description with fewer symbols in it that does the same thing as this Turing machine. We'll call this language min, and to prove that it's not recursively enumerable, we'll assume that it is for contradiction. So because we're assuming min is recursively enumerable, there is an enumerator that enumerates the elements of min. We'll call that enumerator E. So what we can do is we can create a Turing machine called C that gets its own description using the recursion theorem, and it runs E until it finds some machine D with a description longer than C. Now, because min is infinite, there will eventually be a machine D that's longer than C. What it will do next is simulate D on W. So, as a recap, it gets its own description, it finds a Turing machine with a longer description, and then it simulates that machine on W. Min is infinite, so C will eventually find a D that is longer than it. And because C simulates D, they're equivalent to each other. So C is equivalent to D, and it has a shorter description than D, which means that D is not minimal. But D has to be minimal because it was enumerated by E. So there's a contradiction, which means that min is not recursively enumerable. Finally, the recursion theorem can be used to show that every computable function D has a fixed point, where a fixed point is a Turing machine F, such that the Turing machine described by T of F is equivalent to F. So F just is a Turing machine, and when you apply T to its description, you get the description of another Turing machine. And regardless of what T is, regardless of what T does, the output of T on that Turing machine is another Turing machine that has the same behavior as the input. And if the output of T is not a valid Turing machine, it's just treated as a Turing machine that rejects immediately the input. It rejects every input immediately. This fixed point F is shown here. It gets its own description using the recursion theorem. Then it computes T of F, and we'll call the result G. And then it simulates G on W. So because of the recursion theorem, it's able to get itself, and then it's able to compute T on itself to get the new machine, and then it simply simulates G on W. So therefore, it's equivalent to G because it simulates G. So the machine is equivalent to the output of T on itself.
Now we are going to talk about the decidability of logical theories. To understand decidability of logical theories, we need to understand notation and terminology. A model consists of universal set and the relation between the elements of the set. It's denoted as a tuple, where U is the universal set and P1 through Pk are the relations. We also see two examples, where in the first example, N represents the natural numbers and the universal set. The addition represents the relations. In the second example, N again is the universal set and the addition and multiplication are the relation. Next, the terminology is the language of a model. It means the set of all statements including true and false statement. The next terminology is theory of a model. This means only the true statements in the language of the model. Then the next term decidable means if there is an algorithm that decides if the statement of the language of the model is true or false. We also need to have knowledge of how sentences work in order to understand decidability and logical theories. Sentences are built using variables, relations, and symbols. There are three different symbols: Boolean operations, parentheses, and quantifiers. Variables can be denoted in many ways. For example, A, B, C, x1, x2, x3. Relations are denoted as R1, R2, or Rk. For example, here we see for all x and for all y, R1 of xy or R1 of yx. Here R1 doesn't represent anything. We're going to give R1 a meaning using a model. Now we're going to see an example of a model. N less than equal. N is universe, which is the set of natural numbers. Relation R1 is represented with less than equal. The sentence shown here is true in the model because for all x and for all y, R1 of xy means x is less than equal y, or R1 of yx means y is less than or equal x. However, this statement is not true if we use the model n less than. In that case, what we will end up getting is for all x and for all y, R1 of xy means x is less than y, or R1 of yx means y is less than x. So we won't have the case where x and y would be equal. Now, going back to the model n less than equal, instead of writing R1, we can replace it with less than equal. So now we can say for all x and for all y, x is less than equal to y, or y is less than equal to x. Now we're going to talk about theory of natural numbers with addition. The theory of n plus is decidable. There is an algorithm which will decide if a sentence in the model is true or false. So in this model, R1 of xyz means x plus y is equal to z. There is a deterministic finite automata that can also do addition. But input must be in a special form, and that special form is each symbol of the alphabet represents a column of bits. For example, here B is a regular language of our alphabet sigma 3, where the bottom row of each string represents the addition of top and middle row. For example, in the second picture, we see the first row is 0, 1, 1, and the second row is 0, 0, 1, which equals to 1, 0, 0. Thus, we can say this belongs to B. On the third example, we see the top row is 0, 1, and the middle row is 0, 0. Now, it does not equal to 1, 1. Instead, it would have been 0, 1, which does not belong to B.
This is a DFA that solves that language. It actually solves the reverse of the language B, which is fine because any regular language can be reversed and the result is still a regular language. So you could create a DFA that gives the reverse of this language. Since it's in reverse, it's looking at the least significant bit first, and it's working its way towards the most significant bit. At every step, it's comparing the bits in the column to what is in the last row of that column, and it's also considering whether or not it is carrying a bit over from the previous addition. So if at any point the top and the middle row don't correspond to what's in the bottom row, it will be rejected immediately. Otherwise, it will carry if the sum of the first and second bit and the carry bit are greater than 2. If it ends on a bit where it doesn't have to carry, it accepts. If it ends on a bit where it's supposed to carry, then there's overflow, so it does not accept. What this algorithm needs to do is decide whether a formula phi is true. And what this formula phi will look like is q1 x1, q2 x2, and so on until ql xl, and then a formula without any quantifiers in it called psi. Each q sub I is a quantifier. It's either the for all quantifier or an existential quantifier. We also define for each I phi sub I, which is just the same thing as phi with the first I quantifiers shaved off the front of it. So phi of 0 is phi itself because there's no quantifiers taken off, and phi L is the same thing as psi. It's the formula without any quantifiers attached to it. The first step of this algorithm is to build an NFA called AL for phi L, which is the same thing as psi. So this is like the DFA in the last slide. It will accept strings over this generalized alphabet sigma L such that the rows of the string correspond to numbers that make the formula true. So any string where the rows represent numbers that satisfy psi. Remember that psi is made up of components that look like x plus y equals z, and they're joined by and, or, and not, but there's no quantifiers. So these individual additions can be made with DFAs, and they can be joined through the and, or, and not operators using the constructions for union, intersection, and complementation, because regular languages are closed under those operations. So you can make a DFA, or an NFA actually, that will recognize this language. After building the NFA for psi, or for any layer phi sub I, we need to build another NFA that captures the next layer of the formula with an additional quantifier attached to the left of it. So we start with the NFA for phi L, and then phi L minus 1, and so on until phi 0. Each NFA AI uses the alphabet sigma I in contrast with a sub I plus 1, which uses sigma of I plus 1. One of the rows of the alphabet gets removed, so each string has I rows instead of I plus 1. This corresponds to one of the variables getting removed because it is being quantified over. In the case that the quantifier is the existential quantifier, the NFA AI simulates I plus 1, except that since it is missing the bottom row of its input, it non-deterministically guesses what the last row is, and it simulates A of I plus 1 with that guessed value. Therefore, A sub I accepts strings such that there exists some value that would make the formula true. In the case that the quantifier is the universal quantifier, it is converted into the form shown here. It is the negation of the existential quantifier over the negation of the inner formula. For this case, the NFA A sub I plus 1 is first negated. Then the construction is done as it was for the existential quantifier. Then the NFA is again converted into one that accepts the complement of that language. At the very end, an NFA A0 is built, and phi is true if and only if A0 accepts any string. The algorithm simply checks if A0 accepts the empty string. If it does, the formula is accepted. Otherwise, it is rejected. The theory of the natural numbers with addition and multiplication is undecidable, and you can show that it's undecidable using reduction. So given a Turing machine M and a string W, you can use the plus and times relations to construct a formula that says X is a valid accepting computational history of M on W. So the fact that you have both plus and times allows you to check that a natural number X encodes a computational history of M on W. M accepts W if and only if there exists some valid accepting computational history of M on W. So M comma W is in A if and only if there exists an X such that phi of MW. So A reduces to the theory of natural numbers with plus and times, and we've already showed that A is undecidable, so the theory is also undecidable. The undecidability of the theory of the natural numbers with the plus and times relation has important implications for the provability of statements in that theory. A proof pi of a statement phi is a sequence of statements where the last statement is phi itself, and each statement in the sequence follows from the previous statements and axioms. So pi and phi are both strings, and it is decidable whether a string pi is a proof of phi. So it can be decided whether something is a proof of something else. Also, another property is that if phi has a proof, then it is true, and this is called soundness. So if something is provable, then it is true. Even though the theory is not decidable, the set of provable statements in the theory is recursively enumerable. And by provable, I mean that a statement phi is provable if there exists a string pi such that pi is a proof of phi. The algorithm P, as shown here, recognizes the set of provable statements in the theory. So what P does is iterate over all strings pi, and if pi is a proof of phi, it accepts. And the operation on line 4 is valid because it is decidable whether pi is a proof of phi. If some pi is found that is a proof of phi, P accepts that statement, so P accepts any statement with a proof, and P on any statement that doesn't have a proof will loop infinitely. The next part is to show that there exists a statement in the theory of the natural numbers with addition and multiplication that is true but unprovable. And to show this, we assume for contradiction that all true statements in the theory are provable. And now we have to show that under this assumption, the algorithm D, as shown here, decides the theory. But this can't be because the theory is undecidable. This algorithm D will run in parallel P on phi and not phi. If P accepts phi, it accepts. If P accepts not phi, it rejects. Because either phi or not phi is true, one of them has to be a provable by assumption, since we assumed that all true statements are provable. So P will either halt on phi or it'll halt on not phi, whichever is provable. And if P accepts phi, then it is provable and therefore true because of soundness. And if P rejects phi, then not phi is provable and phi is thus false, again because of soundness. So this algorithm D is able to decide if phi is true or false, and therefore the theory is decidable. But again, the theory is undecidable, so in conclusion, there exists a true but unprovable statement in the theory. So you can't prove everything that is true. It's possible to construct a specific sentence that is true but not provable. We can define it in terms of a program S that will be described in a moment. The statement that is not provable says that there is no valid accepting computational history of this program S on the input 0, and 0 is chosen arbitrarily. This psi is true if and only if 0 is not in the language of S. So this S is an algorithm that gets its own description using the recursion theorem. It builds the sentence that we just described, psi, and it runs P on psi. If P accepts, then S accepts. If psi is provable, then P will accept psi, and S will thus accept all inputs, and in particular 0. So therefore, psi is false and therefore unprovable, which is a contradiction. This means that psi is unprovable, which also indicates that P does not halt on psi, so S does not halt on 0, which means that psi is true. In conclusion, the statement psi is true but unprovable. And that concludes the decidability of logical theories. Thank you for listening.